All right, starting lesson 3.2, we're working with logarithmic functions and their graphs. Now the inverse of the exponential function, a to the x, is called the logarithmic function. That's where logarithms come from, by obtaining the inverse of an exponential function. Okay, so here we have log, and then we have this little a, big X. All right, that's read log of x base a. The little value is your base. Okay, and logarithmic and exponential equations are interchangeable. So if you look at this here, we could convert from one form easily into the other. All right, just by doing this, check this out. Here's the base for the log. All you do is take that base and raise it to the power of whatever's on the other side of the equation. All right, then it's equal to the variable you were taking the log of. All right, simple as that. So, all right, now important note, bases are the same both in logarithmic and exponential form. All right, what does that mean exactly? Here's the base for our log. Here's the base for our exponent. All right, it's the same in both forms. And a couple other things to take note of. You cannot take the log of a negative number. That does not work. All right, now the most common logarithm has a base 10. And if there is no base for the logarithm, for example, like log 5, then that means that the base is 10. All right, if nothing's there, that means the base is 10. All right, let's do a couple examples. All right, example 1, convert to exponential form. So I just take the base here for that log, and I raise it to the 4th power, and that's equal to whatever you were taking the log of, 81. And yes, that's true. All right, so here we have 10, raise it to the negative 3 power. All right, so you have that equal to 1 over 1,000. Okay, that's all you're doing here, is converting it to another form. All right, and 10 to the negative 3 power is 1 over 10 to the 3rd power, which is 1 over 1,000. All right, example 2, solve without a calculator. All right, so I'm evaluating here. I have to plug in the 4. All right, f of x is the same thing as y. Okay, what's next? Nothing much I could do here. It's in logarithmic form. Okay, it's in logarithmic form. Let's convert it into exponential form. 16 to the y power is equal to 4. Okay, now what can we do? Well, if I could get these bases to be the same, that would help. So I could write 16 as 4 to the 2nd power. All right, then it's to the y power equals 4. And I'm going to go down here a little bit. All right, so now I can multiply these. And I have 4 to the 2y power equals 4. Okay, cool. So I have the same bases here now. Now I could set the exponents equal. Wait, there's no exponent here, but that's okay. If there's no exponent there, it's always 1. So then you could say 2y is equal to 1. Divide by 2, and we have now solved for y. Y is equal to a half. On to the next example. Same deal as before. Let's evaluate it. Let's plug in the x value. So it's y is equal to log of 1 over 500. All right, here they tell you that you can use a calculator. So go ahead, punch that into your calculator, and you get negative 2.699. All right, let's go on to the next example. Convert to logarithmic form. Okay, how do you go from exponential to logarithmic? All right, now, as I said before, the bases for both forms are always the same. So the base of this exponent's 8. So the base for my log is going to be 8. All right, and it's going to be of whatever numbers over there by itself. Log of 64 base 8. And what ends up on the other side is the exponent that you had originally. Okay, and we're done here. All right, just as a little side note, here's something you could do. This property is going to come up in the future, but I just want to throw it out there. Maybe you'll find it useful. If I want to convert to logarithmic form, I'm going to take log of both sides, and I'm going to intentionally use log base 8. All right, because when I do that, here I have this log of 8 base 8. And essentially, you could think of it as it disappears and the 2 just drops down. And so you have log of 64 base 8, just like we have up here. All right, so you could use that property if you like. Maybe it'll make more sense to some people, up to you, but just showing you different methods. All right, for part B, my base is 9, so it's log base 9, and it's log of whatever's on the other side here from the exponent, 27, and that's equal to whatever the exponent was, 3/2. All right. Going on to the next example. All right, the natural logarithm. Okay, where does that come from? If you ever see ln, that's the natural logarithm. Now, where do you get that from? You get it from having a log that has a base e. So if you see this, then you could rewrite that as this. Okay? All right, so example 4, it says to convert to exponential form. All right, how am I going to do that? I have no base here. Okay, well, there actually is a base since it's natural log. You could rewrite it as log base e. Okay. And now I'm going to apply my process of converting it into exponential form. Take the base, raise it to whatever's on the other side, and it's equal to 2/5. That's all there is to that. All right, convert to logarithmic form. All right, so here's the base for the exponent. So that's what the base of the log is going to be. And now I'm taking the log of whatever's on the other side. So log of 7.3890, and that's equal to whatever my exponent is, 2. All right, done with that. On to the next example. Okay, now here we have a bunch of logarithm properties. Now, this is just regular logarithm. This is natural logarithm. Now, all these properties are the same as the ones over here, okay? So this is what we have to work with. If you're taking the log of the number 1, that's always equal to 0, okay? And just like a to the 0th power, anything to the 0th power is equal to 1. All right, but whenever you take the log of 1, it's equal to 0. Now here I have the log of a base a. So if whatever I'm taking the log of here, matches the base that I have, that's equal to 1. So you could think of it almost as it sort of cancels out. Not really, but it's equal to 1. All right, then here I have log of a to the x, and then the base is a. So once again, whatever I'm taking the log of, its base is a, and the base of the log is a. So this x just sort of drops down. That's one way to look at it. And here I have a raised to the log base a power. Once again, the bases are the same. Whenever that happens, you could just think of it as it poof, disappears, and that variable just drops down. All right, then here I have log of x base a. Here I have log of y base a. Since the logs have the same bases, then whenever I'm taking the log of, they must be equal to each other. All right, so get familiar with these properties. You're going to use them very often. Example 5, simplify. Note, it may help to set the expression equal to x. Okay, so here I have log of 1 base 1.5. Okay, how am I going to solve this? I don't know. Well, you know that log of 1, regardless of what the base is equal to what? 0. You could have done it a different way. You could have set it equal to x, because it's equal to something, and figure out what that something is. So convert it into exponential form. 1.5 to the x power equals 1. And then just ask yourself, well, what would the exponent have to be in order to obtain a result that's 1? Well, if I raise it to the 0th power, then I will get 1. So x must be 0. All right, so there's different ways to look at it. All right, for the next problem, here I have an exponent. The base is 9, and the log is base 9. So essentially, boom, that disappears, and the 5 drops down. That's one way to think about it. All right, going on to the next examples. Evaluate with a calculator. All you have to do is plug it in. All right, plug it in your calculator and we get negative 3.418. All right, if you need any help with the calculator, please make sure to ask. All right, for the next one, solve without a calculator. Okay, how am I going to simplify this? Well, I could take the natural log here and rewrite it as log base e, and then I have this still, e negative 2. All right, once again, this is the same as this. All right, and then since what I'm taking the log of has the same base as my logarithm, all right, these just sort of cancel out, disappears, and what drops down? Then negative 2. All right, on to the next example, part C. We have log of x minus 3 base 2 is equal to log of 9 base 2. Since the logs have the same bases, I could set whatever I'm taking the log of on each side equal to each other. I'll just add 3 here, and log is equal to, oops, not log. All right. X is equal to 12. All right, couple more examples. Okay, graphing logarithms. The inverse function of an exponential function with base A is a logarithmic function with base A. Okay, so this is what you learned in the previous lesson, right? Exponential function. There's the starting point, all right? And it has a horizontal asymptote. All right, now inverse, if you recall from the previous chapters, when you want to find the inverse of a function, when you're graphing, all you have to do is reflect it over the line y equals x. All right, refreshing the memory there. All right, now if you reflect it, you get this graph here. All right, now let's study the properties of this graph. All right, so here's its starting point right there. Instead of 0, 1 for an exponential function, we now have 1, 0, all right, as its starting point. And instead of having a horizontal asymptote, it has a vertical asymptote. And all the same stuff applies to the natural logarithm as well, okay? Same deal. All right, nothing's different, just different base e. All right, so the parent logarithmic function, the most basic logarithmic function, what is its domain? All right, well, here's the vertical asymptote, right, at 0. So the domain is going to start at 0, and it's going to go, keeps going this way, right? So it's going to go off to infinity. Then the x-intercept, all right, when y is equal to 0, what's your x value? 1. All right, there it is right there, x-intercept. And then you have the vertical asymptote, which we stated previously, and how you describe that, that's the equation x equals 0. All right, let's do a couple problems involving graphing. All right, find the domain, the x-intercept, and vertical asymptote of the logarithmic function and sketch its graph. Okay, here we have a very basic logarithmic function. The base, you don't really have to worry about that, okay? You're just worried about if you're adding or subtracting values from this expression. In this case, we're not doing that, so not much is happening with this graph. Okay, well, I know since this is a parent logarithmic function, then the the x-intercept is going to be right here. 1, 0. Now, how do you know it's 1, 0? Well, plug in 1 for x. You're going to have log of 1 base 6. And what's that equal to? When you take the log of 1, what's it equal to, regardless of the base? It's equal to 0. Okay, so there's your y value. All right, and then let's fill this in here. Okay, then I have the vertical asymptote. Well, that's going to be just 1 unit to the left of the starting point. It's x equals 0. And then the domain, what's the domain going to be? Well, the graph hugs up against the asymptote, passes through the x-intercept, and then goes to the right forever. So it starts at an x value of 0, not including 0 though, and it goes on to infinity. All right, let's do another example. All right, if you're adding a value to the x inside here, if it's attached to it, then whatever you're doing to it, you do the opposite in terms of movement. All right, horizontally. So normally I would start here, all right, and I'm gonna make my graph in red, but I'm adding one here, so essentially I have to go to the left one. All right, so everything shifts to the left one. All right, so now my x-intercept is at 0, 0. And my vertical asymptote is also just 1 unit to the left of the starting point. So instead of being at x equals 0, now it's x equals -1. Instead of my domain starting at 0, it now starts at -1, and it goes, the graph goes on to infinity. All right, so here I am, passing through the x-intercept, and off to infinity. Okay, if you understand the very basic function, okay, if you understand the very basic function and its components, meaning the starting point and the asymptote, then it's super easy to graph these functions. All right, make sure to ask for help if you need it. Begin the assignment at the bottom of the web page.